Okay, so I'd like to talk about Dynkin diagrams today. So last time I talked about Coxeter diagrams, which are a relative of these. The Coxeter diagrams we saw are used to classify finite reflection groups, that is, finite groups of linear transformations of Rn that are generated by reflections along various vectors. And those are the manageable finite groups in many nice ways, and they tend to be symmetries of beautiful geometrical structures in Rn, like platonic solids or higher dimensional versions of platonic solids, or some generalizations of those. But very often, we want to think about those groups acting as transformations of a lattice in Rn. So a lattice, what's that? So a lattice, let's call it L in Rn, is a subset that looks like this. So you take any old basis of Rn, say Vi, and then you take linear combinations of those basis vectors where the coefficients are just integers. And so you get a picture that looks something like this. We could take in R2, we could take two basis vectors, and then taking all integer linear combinations of them, we get points that look like this, which is why it's called a lattice. So there's a highbrow way of saying the same business. We could say a lattice in a finite dimensional vector space is a subgroup that's a free abelian group. So this is a free abelian group with these as generators, but we want it to be a free abelian group of rank n if you have an n-dimensional vector space. So we want to have as many of these VIs as there are dimensions in our vector space.
Are they meant to be linearly independent?
Sorry, I said in words, but not in writing, for some basis. VI in Rn. Yeah, thanks. So, and of course, you'll notice that the same lattice can have different choices of these vectors Vi. So we call these vectors Vi the generators of the lattice. You can say we call them generators of L. And there are different choices of generators. So I could have picked, I could have equally as well picked these vectors here to be generators. Now, it's okay. I want to study lattices that are very symmetrical, that have a finite reflection group as their symmetries. And so we introduced the concept of roots. So we say that these we say that a bunch of generators are roots. If when you reflect along any one of these roots, it maps the lattice to itself. So remember last time I introduced this notation of a linear transformation that reflects along VI, RVI, and we want it to map L to itself of each. I'll give you lots and lots of examples. So not every lattice has roots. And some lattices can have more than one very different kind of choice of roots. So we'll see examples of all that stuff. But I just want to tell you what Dynkin diagrams classify, which is the idea of a lattice. So this definition of mine here is a bit non-standard, I think. But a root lattice for me will be a pair of a lattice and a finite reflection group. So L is a lattice in Rn. And gamma is a finite reflection group. But actually, I'm just about to say something that implies that it's a reflection group. So it's a finite group of transformations of Rn generated by reflections along some roots.
John,
Yeah,
there's a question on Zoom. What does reflection along mean here?
did I say through last week or along? So I forget what do you call that kind of verb? Anyway, I said what it was last time. So RV, I'm calling it reflection along V. It's the linear transformation characterized by the property that it sends V to negative V, and it leaves fixed all vectors that are orthogonal to V. Maybe I said through last time for this, but so it's just flipping V to negative V and keeping everything orthogonal to it. Right angles, so this is an orthogonal transformation of Rn. It's uniquely specified by that. Okay, so we want a finite group generated by reflections Vi for some roots Vi of our lattice. So for some collection of generators that map the lattice, whose reflections map the lattice to itself, you get a finite group gamma. And of course, just from the way it's all set up, gamma will preserve L, right? So gamma will act on L. Because each of these reflections maps L to itself. The order of the quantifiers, like there exists and so on, matter a lot in this business. When you actually start trying to really get careful. So let me just give you a bunch of examples, though, to illustrate the kind of things that happen. So we classified finite reflection groups last time in terms of Coxeter diagrams. So one thing you can do is take a Coxeter diagram, get the group from it, and then see if there's a lattice that gives you a root lattice. But you notice various things when you do this. So first of all, so some choices of gamma, I'm just going to use gamma to mean a finite reflection group, have no lattice that they preserve. So here's a theorem to that effect that sort of shows you what goes wrong. So no lattice in any Rn has n-fold rotation symmetry, rotations around some axis, rotations in some hyperplane, I should say, unless n is 1, 2, 3, 4, or 6. So you may have noticed when you looked at like tiles and wallpaper and stuff that you often see squares, you often see triangles, like equilateral triangles, you often see hexagons, like honeycombs, hexagons, but you never see pentagons if you're looking for a regular lattice, and you never see 7-gons or anything. So this fact, which I'm going to prove in the case, I'm going to show you what goes wrong in the case n equals 5 in a second, but this fact is that this is enough to rule out certain finite reflection groups. And those are the ones that have rotation symmetries of order 5, 7, 8, or so on. So remember, there's this guy here called H2, which is the symmetry group of a regular pentagon. So it has 5-fold rotational symmetries within it. And so that can't show up as the group as part of a root lattice.
Quick question.
Yep.
Rn and n-fold rotation, they're really the same.
No, they're not. M. Probably this is why the letter M was first invented. So yeah, thanks. The symmetry group of the dodecahedron or icosahedron also has 5-fold symmetry, which you can see straight from that 5 there. And also, remember, I said there's this 4-dimensional generalization or analog of the icosahedron and dodecahedron. The symmetry group is this group of transformations of R4. And so that one's also ruled out. And then finally, there are a whole bunch called IN. These are all symmetry groups of the in the plane, but this is the symmetry group of the regular n-gon. And so I'm saying that that's out when n is equal to 7. When n is equal to 5, it's this one here, but we just call it, we call these a little different name than that. So those guys are out. So I gave you this big list of Coxeter diagrams, and I'm saying that the ones that have any numbers on their edges, except for these numbers, are out. It's fun to see the proof of that, of this fact, but well, it's actually really fun to see it in the special case of n equals 5, where there's like a really beautiful proof. The same idea would work for the higher cases, but n equals 5 is particularly attractive.
John, there's a question on Zoom. In the theorem on the right,
Yeah.
Is it really Rn rather than R2?
Yeah, I want to. Yeah, I mean,
Okay.
yeah. So, yeah, I mean, like this is like an R4 kind of thing. Yeah, I mean, when I talk about rotational symmetry, what I mean is that you're taking Rn and you're writing it as an orthogonal sum of R2 and some other Rn minus 2. And the transformations fix that orthogonal part and just do a rotation in the plane. So what really just matters is the plane, but I wanted to state it more generally so that I say that, like, whenever you see a Coxeter diagram that has like a 5, 6, or sorry, 5, 7, etc. in it, it's out. So here's the proof, but there's the proof. This is like for, okay, this is like the proof for n equals 5. And I'm just going to draw the case when n dimension is 2, but it automatically covers the other ones for what I said. So suppose we had a lattice with 5-fold symmetry. Okay, so it would have a vector in it, and then you could rotate that vector rotationally and get a total of 5 vectors. So it'd have to have all these points in it, right? And then what you can do is you can draw this, which is of course sort of a satanic symbol, or at least was actually a Pythagorean symbol, but the Christians didn't like the Pythagoreans. So what's the point of this thing? Well, notice if this point is in the lattice and this point is in the lattice, because the lattice is closed under addition and subtraction, then this vector here, thought of as a vector, is in the lattice. And so you can add this vector to anything in the lattice and get another thing in the lattice. So in particular, we can add this vector to this point here. And where do we get? we get over here, you'll notice there's a parallelogram here, right? So this point has got to be in the lattice as well, because it's this point plus this vector. And by the same type of argument, you see that all these points have to be in the lattice. But if we pick this vector to be the smallest non-zero, the shortest non-zero vector in our lattice, then we get a contradiction because now we find even shorter ones. So that's the proof by contradiction. So this is the proof. A very nice proof. There's a lot of words that went along with that picture, but I'm too tired to write them down. Okay, so you could like do similar type of proof for other m. So that's one kind of thing that can happen. But then another kind of thing that can happen is that sometimes the same lattice will be able to get along with different finite reflection groups. That is, sometimes you can get a root lattice in two different ways from the same lattice. So some lattices can give you root lattices with more than one finite reflection group. So here's a very simple example. Just take the square lattice in the plane. So this lattice, you can think of it as z squared sitting inside r squared. Or another fun way to think about it is you could think of it as all the numbers of the form a plus bi in the complex plane. So you could take the integers and adjoin I and get a subring of the complex numbers. And that's what this thing looks like. And this is called the Gaussian integers. So Gauss started generalizing number theory to various subrings of the complex numbers. And this is like the first one that he thought of because it's sort of the super obvious one. And you can notice that we can make this into a root lattice in more than one way. We could pick these vectors as our basis, or as our generators for this lattice. There's sort of obvious vectors at right angles to each other. And then they are generators of the lattice, and their reflection through them preserves the lattice. So you get a root lattice this way. And if you just look at what the finite reflection group is, it's the group called A1 times A1. That's a finite reflection group whose Coxeter diagram just consists of these two dots with no line connecting them, meaning that these two reflections here commute with each other. Remember, when you have an edge labeled with a 2, it means that the two reflections commute, but we just don't draw the edges labeled with a 2. So this thing here is the symmetry group. It's not the full symmetry group of this lattice. It's just the symmetry group, for example, of a rectangle. It's just the symmetry group Z mod 2 times Z mod 2. Abstractly, it's Z mod 2. So that's one way you can make this thing, this lattice, into a real lattice. But that's a sort of boring way because it's such a small group. But there's a more exciting way, which I talked about last time when I was talking about the symmetries of the square, which is that you could take a different pair of generators for the lattice, namely this vector v1 here and this vector here, which maybe I'll call v2 prime or something. So now there's a 45-degree angle between them. And so now the Coxeter group we get is one that I talked about last time called BC2. It's two dots with a 4 there. And this is the whole symmetry group of the square. So that's another root lattice with the same lattice, just a different Coxeter group. just a different finite reflection group. So that kind of thing can happen and does a lot. Let me just mention like another case where it happens that's really nice. So in addition to the Gaussian integers, there's another extremely charismatic subring of the complex numbers. I think Gauss had a student named Eisenstein, and the Eisenstein integers are what you get when you look at a hexagonal lattice. So like here's 0, here's 1, but this number here is e to the 2 pi I over 3 now. And if you look at the lattice generated, you don't like that? Is it 2 pi? Tom's making me nervous. That's pi I over 3, which is probably actually what I want to talk about though. And you could do it with 2 pi I over 3, that looks different. That's the one over there. That's a different choice of generator. So I want to take these two guys. So this is an angle here of pi over 3. So one way to think about this is it's the integers adjoin e to the pi I over 3. And these are called the Eisenstein integers. And it's again, it's a subring of the complex numbers. So it's not just a lattice, it's sort of better than a lattice. And it's extremely important in number theory as well. And so here, this is giving us this choice of roots here is giving us this Coxeter diagram called the A2 Coxeter diagram. That's 3 is just coming from this pi over 3 here. And so this is the symmetry group. If you work it out, it's actually, you can think of it as the symmetry group of an equilateral triangle. For example, this equilateral triangle here, say. So that's one way to make the Eisenstein integers, that lattice, into a root lattice. But there's another way to make the same lattice into a root lattice by picking different roots, different choice of generators. Because you could also, I'll keep using the vector, I'm calling them by their names as complex numbers now. I could keep using the vector of 1, but I could use this guy here, which is at an angle pi over 6 from 1. I don't want to figure out the formula for it. Well, I can. It's just 1 plus that other number. And so those are still generators, but now they have a different angle between them. And so this is the Dynkin diagram that's called the Coxeter diagram called G2, which has a 6 here. And so this is the symmetry group of the hexagon, of a regular hexagon. So you get more symmetries, you get twice as many symmetries when you include reflections through that guy. So, okay, so those are various ways in which you can have the same lattice, but different amounts of symmetry, making it into a root lattice by choosing different generators that happen to be roots. But there's another thing that can happen too. All these things that can happen, this is like the third thing that can happen, are things that are going to make the classification of root lattices be a bit different than the Coxeter diagrams. What we will do is classify these root lattices using something called Dynkin diagrams, which are like Coxeter diagrams, but they're different because they have to deal with these issues that I'm raising here. And the third issue is that sometimes the same finite reflection group can go with different lattices to give different root lattices. Now, when I say different root lattices, I mean really different. So not a very easy way to change a
a lattice is just to like rotate it, or even more benignly, you could just expand it or shrink it, and then it would have the exact same group of symmetries. So when I say different, I mean really different. So not up just up to like rotations and rescaling. And there's basically one bunch of examples where this happens. So you may remember I have these Coxeter diagrams with a funny name BCN. And that's because these BCN guys, which were the symmetry groups of the cubes in various dimensions, the hypercubes, actually give you root lattices in two different ways called BN and CN. So the BCN group will go with the BN and the CN lattices. Well, let me say how that works. So the BN lattice is a very banal lattice. So BN lattice, it's just Z to the n. So it's just vectors in Rn where every entry is an integer. But then we've got to get a root lattice, we've got to pick some generators for this that are roots. And there are various ways to do that. But the interesting way is this. So choose these roots. This is not at all obvious. 1, 0, 0, 0. But then instead of doing like 0, 1, 0, 0, which would give us something very boring, we could do that. But what we're going to do is 1, 1, 0, 0, 0. And then we'll just keep on sliding them back like that. So I actually already showed you this last time when I was describing the symmetries of the cube. I picked 3 different vectors, and reflections through those 3 different vectors generated the symmetry group of the cube. And those 3 vectors were these first 3, but where I was just in 3 dimensions, so there was no dot, dot, dot stuff. So we can do this kind of thing. And if you look at it, you see that the angle between these 2 vectors is 45 degrees, whereas the angles between any successive ones of these next to each other is pi over 3, 60 degrees. So you get, so the Coxeter group that you get generated by these reflections along these vectors has this look. Here I just stopped it 1, 2, 3, 4, 5. So this would be like in the case of a 5-dimensional space, it would look like this. But otherwise, you just get more. Sorry, sorry, 4. So the idea is that like here is reflection along this one, and that vector is at 45-degree angle to this next one here. But then this next one is at just a 60-degree angle to the next one, and so on and so on and so on. So you'll notice that these vectors aren't all the same length. This guy here is shorter than all the rest, and so we denote this choice of lattice and finite reflection group. Well, first of all, we call it BN. So it's one of the 2 ways to pick a lattice that has this BCN finite reflection group as its partner to make a root lattice. And we use this diagram
to keep track of it. So what we'll do, it's sort of ad hoc, is that because this dot here is a vector that's longer than that one, we do a little greater than sign here. And then you're supposed to somehow know that this double-edged arrow means a 4, okay? So a single-edged arrow in this notation, this new notation, which is the Dynkin diagram notation, means 3. And this double-edged thing means a 4. Remember, when we in the game we're doing now, the only labels on edges that we could ever see are well, 1, 2, 3, 4, or 6. Because because we can't have like 5-fold, etc., rotational symmetry. So when it's a 2, we just don't draw an edge at all. When it's a 3, we draw a single edge. When it's a 4, we draw a double edge, and when it's a 6, we'll draw a triple edge. So it's just some stupid way to simultaneously draw the BCM Coxeter diagram, but also indicate something about this lattice. Let me show you what's going on here. So let's do the case where like n is equal to 3. So I'm just going to draw a little portion of the lattice. I'm just going to draw some of the lattice points. So I'm going to draw a bunch of lattice points in 3 dimensions. These are just points whose coordinates are all integers. I mean, I'm drawing some of them, just the cube's worth of them. And in the middle there of that cube is the origin. And so this vector 1, 0, 0, that's this one here. And then this vector 1, 1, 0, that's this vector. Maybe I should draw it behind. That's this vector going back here. That's at 45 degrees. And then this third vector, 0, 1, 1. That's this one here. And I drew all this in a slightly different way last time. And so you can see that the angles between these vectors work out, right? Like U is right angles to W, U to V is a 45-degree angle, and V to W is a 60-degree angle. So this is a picture of some roots for the BM lattice. And if you think about it, you see the reflections along those generate all the symmetries of that cube there. But now there's another thing we can do. We can keep the same group, but pick a different lattice. This is the only case where this weirdness happens. And so there's another lattice called the CN lattice. It will give us another root lattice, but with the same symmetry group. And here what we do is we don't take this many, we don't take all these vectors. We just take vectors with integer coordinates where the sum of the coordinates is even. So it's in 2z, so it's an even number. So in particular, you'll notice that B and W will still be in there, but U will not. And so what we have to do, or what we can do, we can get roots where we start with 2, 0, 0, and then 0, 1, 1. These dot dot dots mean zeros. And so on. So the only thing we did here is we doubled our first vector. Since we just doubled our first vector, reflection along it does the exact same thing. So we get the exact same group generated by those reflections. So the group is still this group that we are calling BCN. The finite reflection group is still
is still the same. But we've got a different lattice now. And once I draw it, you'll sort of see that it's not just like a rescaled version of the original lattice. It's just a truly different lattice. And so people make up a different notation for this. They call this, well, I already said it, this lattice is called CN. But we also make up some goofy diagram notation for this lattice, which indicates that now this funny vector is longer than all the rest instead of shorter. So instead of drawing an inequality symbol the way we had before, we draw it this way here. So this is the picture mnemonic for what's going on here. So let me show you what happens, what's going on here. So basically what's going on here is that it's less connected to a cube and a bit more connected to an octahedron in 3 dimensions.
There's a question on Zoom.
Sure.
Should there be 11000 as well?
1, 1. Oh, did I screw up? Yes, I did. Thanks very much. Thanks for catching that. Yeah, I didn't want to change anything from what I had before, except doubling the first vector. So yeah, I still include this guy that's at 45 degrees to it. Thanks a lot. That's important. Yeah. Good. Thanks for catching me there. Yeah, otherwise we just wouldn't be getting this picture here. This Coxeter diagram here. So this is the picture that's the hardest one for me to draw, but I'll try it. So I'll start by drawing that cube that I just erased. So this is a cube whose corners and faces and edges, midpoints of edges are all vectors with integer coordinates. But now I want to draw this vector 2, 0, 0, which will be over here somewhere. And this vector 0. Well, when you start doing linear combinations of these, you see what other vectors you get. And so you have to take my word for it that we'll also get this vector 0, 0, 2 up here, and we'll get a vector in front of a cube and a vector to the left of the cube and a vector down below the cube. All of these are vectors that has one coordinate being plus or minus 2 and the other 2 are 0. And these guys here that I'm drawing here, they're the corners of an octahedron, because basically I've taken like the points in the center of the cube and I've just doubled their coordinate and moved them out like that. And so if I draw this octahedron, and I've been practicing this all week, so this is actually the hardest thing in the whole damn lecture. The interesting thing is that the edges of this octahedron that we get, they hit the midpoints of the edges of the cube perfectly. Well, perfectly if I could draw it perfectly. It seems to so far be succeeding. It's sort of amazing. So in particular, like it will hit this one. This is like the hard one. It goes, well, okay. Not too late to save the day there. And then this thing hits this right in the midpoint. Well, not quite the midpoint, but close enough. And then down here, and then here. This actually probably sort of sneaks around behind and pops out right here. And then I don't have to draw that shaded. That's supposed to be visible. And then here, this actually really goes behind and goes here, but it crosses. Oh, that one's like the terrible one. I don't want to even try to figure out where that looks like it's a complete failure. Luckily, it's behind the cube, so you can't see how badly I drew that. So this lattice that we're getting here, if you look at it, all the dots that I've drawn that are nice and fat are points where their coordinates are integers and they sum to an even number. So like the corners of the cube, like 1, 1, 1, that doesn't sum to an even number. So the corners of the cube, none of the corners of the cube are in there, but the corners of the octahedron are in there. So that's the idea. And so then the roots that we're taking here now, these roots, this vector here. So this is 2, 0, 0. And then whoa,
Oh no, yeah, so like you can barely see it, but there is a thing going back there, it's back there, and so. Just a root here, which is 1, 1, 0. And then there's the midpoint of this edge, which I forgot to draw, but that's another point whose coordinates are integers and sum to an even number. That's 0, 1, 1. So the symmetry group of the cube is the same as the symmetry group of the octahedron. So the same finite reflection group that we had before is the one we have now, and so it's acting as symmetries of this octahedron. But we have a different lattice that's more, it's sort of half as dense as the one we had before, because now the coordinates have to sum to even integers. Okay, so that was the high point of the talk as far as pictures go. But then there's this theorem which says that every root lattice is similar, by which I mean you can get it by rotating and expanding or shrinking to a direct sum of ones like these, direct sum of these. So you can take direct sums of or products of groups, and you can take direct sums of lattices, so you can like build up new ones out of these basic ones in this other boring way. But the interesting ones are the ones that have connected Dynkin diagrams. And so here is our friend AN that we saw before. It's the symmetry group of the N simplex, and I'm not going to tell you now what the lattice is that goes along with it, but there is a lattice giving you a root lattice. Here's our friend Bn that we just looked at, and now we've just drawn it using this funny diagram. So these are Dynkin diagrams coming from these. I'm defining Dynkin diagram, I guess. You get that guy. You get these ones, Dn. Things like this. Interestingly, this Dn guy, it has the same lattice as Cn. But remember, I told you last time that Dn is the symmetry group of the demi-cube. So from a cube, you can get a demi-cube by just taking every other vertex. And so you get a symmetry group that's half as big. So you don't get like the full symmetry group of the cube in this case, but just a group that's half as big. So that's another case where the same lattice can get along with more than one finite reflection group to give you a root lattice. Then we've got our friends E6, E7, and E8, which I would love to tell you in excruciating detail about. I might not today. We've got our friend F4. F4, remember, as a Coxeter diagram went 3, 4, 3. Because of the 4 in here, one of those vectors, one of those roots has got to be longer than the other. We could just sort of arbitrarily pick this one to be longer. If I picked the other direction on this inequality sign, I'd get a picture that was just a symmetrical version of the same picture. So it's not really anything different. So here, the lattice is again very beautiful lattice. You can think of this lattice as a bunch of quaternions. This is a four-dimensional lattice. So instead of using complex numbers, we can use the quaternions. So you can think of them as quaternions where these coefficients here are either all integers or they're all integers plus a half. I could also rescale this by a factor of 2 and say that they're all whatever. I could rescale it by a factor of 2. I hadn't been using a halves so far, but this is actually nice the way I'm saying it now, because this thing here, this bunch of quaternions is really important. Turns out that these quaternions form a subring of the quaternions. If you multiply 2 of this type, you get another one of the same type. So these are called the Hurwitz integral quaternions. And they're a subring of the quaternions. I guess the quaternions are called H. So H doesn't stand for Hurwitz, it stands for Hamilton. So this is sort of like a quaternion version of like the Gaussian or Eisenstein integers. It's a very nice thing. And then it has like number theory significance as well as geometry significance. And that's it. That's all of them. So the other Coxeter diagrams that I had listed all have 5s, 7s, 8s, or so on their edges. So they're ruled out. So these are the only options. And so the only really exciting new thing that happened is that the BCN split into 2 different root lattices.
Is there a G there?
Oh, whoops. Sorry. Horrible. That's terrible. I forgot. Beautiful guy. So this guy, when it was a Coxeter group, when it was a Coxeter diagram, it was 2 dots with a 6 on them. So this is as a group, it's just the symmetry group of the hexagon. And so that 6 gets replaced by 3 edges due to somebody's obscure decision for how to draw these things. Yeah, thanks. Phew, that would be terrible to leave out that one. And that really is all of them. Yeah. Let's see. Yeah, I should just ask. So are there questions or comments about this stuff? That's the theorem, and as usual, I'm not making no attempt to prove it. Yeah.
It's the reason we take halves, because half has length 1.
Yeah, what's nice about this is that if we take the shortest non-zero vectors in here, we get, let me just write them in like an R4 notation instead of quaternion notation. So we get this thing, these vectors, and the various ways of permuting the 4 indices. So that gives us that is, there are 4 places you could put that plus or minus 1. So we get like 8 vectors like that are all of length 1. But then we also get a bunch of vectors like this. And the cool thing about 4 dimensions is that the length of this vector is also 1, because 4 times a fourth is 1. And so there are 16 of these guys too. So it turns out that there are 24 vectors that are all the shortest vectors in here. And so I said last time that this symmetry group called F4 was the symmetry group of some 4-dimensional regular polytope that had 24 vertices. And these are the 24 vertices here. And by the way, all of these guys are roots. So in other words, reflecting along any one of these vectors is a symmetry of this whole lattice. So that's, yeah, so it's a really a wonderful thing. There's like a lot that you can do with that thing. Yeah.
Totally kooky question, but does that have anything to do with spin?
What, this F4?
Well, the fact that you have integers, half integers,
No, not particularly tough to do. I could make up something that this has to do with spin, because everything's connected, but no, it wouldn't be about them being half integers. No, it's just that, no. No. The unit quaternions, SU2, has tons to do with spins, and so these 24 guys are like a 24 element subgroup of like the group of symmetries of a spin 1/2 particle. So it is connected to spin, but in some other funny way, yeah. Yep.
So with the Coxeter diagrams, I think you could take any graph, even if it wasn't one of the ones you showed, and it will define some group. Some reflection group. Is there a similar thing here where each like graph of this form would define a lattice, or is it just a convention?
They certainly don't define a lattice in the normal sense of a lattice. You could try to do something. So like the first case that like where you like run into trouble would be like this 5 guy that we saw. So for example, I didn't emphasize it, but in the way things work in Dynkin diagrams, we have these allowed choices. Let me just use the Coxeter number. We have like 3 is okay, 4 is okay, 6 is okay, but 5 for some reason is out. And so for the 3 case, we get this triangular lattice. And I'm picking 2 roots and they're the same length. For the 4 case, I'm picking 2 roots. And one of them is like square root of 2 times as long as the other. And then for the 6 case, it was something else, which I didn't reveal. But if I'm not too confused, so I'm taking the same lattice, but I'm picking like a different basis vector. This guy, I believe, is like square root of 3 times as long as that. And so the fact that this is like square root of 1 times as long, this is square root of 2 times as long, and this is square root of 3 times as long. But by the way, that is some kind of justification in your Dynkin diagram notation for this type of picture here. So this means like this guy is square root of 3 times as long as that. Okay, but this 5 guy is like breaking out of that pattern. So you could still do what I was starting to show you, namely you could take a regular pentagon and take two vectors from its center to corners. And then you could take a subgroup generated by these 2 vectors. So you could take all integer linear combinations of those. But what I showed you was that subgroup that we'd get would be dense in the plane. So it's not nothing, but it's not what we traditionally call a lattice. So I don't really fully know the answer to your question, but I think like one direction you could try to go in is to say like, okay, we're just going to allow things that are dense in Rn instead of lattices. That would be a thing to try. I haven't really thought about it. There are other issues and other tricks people do try. Yeah.
So I guess what I was actually asking is, if you take these alloyed edges, 3, 4, and 6 ones, like, can you compose them together and make some?
Oh, it's something like that.
Out of them? And will you still get a lattice by like picking them together?
You certainly don't get a lattice that has this Coxeter group. Well, I remember these sorry, say Coxeter group. What I mean by Coxeter group is these pictures can be thought of as recipes for describing a presentation of a group. So you could hope that, oh, you get a lattice with this group as its symmetries. And you definitely don't, because this theorem says that there just aren't lattices with that symmetry group. So I guess you sort of have to. So there are different things you could do, and I don't really fully know the answer to your question. So like one thing people definitely do is they say, well, look, this is still a presentation of a group. And so people study those groups abstractly and call them Coxeter groups. I guess another thing you could do is you could try to actually think of that. It's going to be an infinite group. That's sort of the problem with it in some sense. But you could still try to think of it as being like a subgroup of transformations of Rn. I don't even know if that works. I have bad feeling about that. There are lots of Coxeter diagrams that people don't use to think of as giving you symmetries of Euclidean Rn, but because they're like a little bit too hairy, a little bit too big or something like that. And there's like a whole bunch of them called hyperbolic Coxeter groups that give you beautiful groups of transformations of the hyperbolic plane or hyperbolic space. So this might be, I can't memorize all the hyperbolic Coxeter diagrams, but for example, it could be like really nice group of transformations of hyperbolic free space. In Wikipedia, there are certain somewhat crazed but lovable editors who have decided to take like all the Coxeter diagrams and create a Wikipedia page about each one of them. So, well, at least like the ones that like generate transformations of hyperbolic space or something like that. So you can find beautiful pictures of some patterns in hyperbolic free space that go along with some Coxeter diagram. So yeah, so I don't really know the best answer to your question, which would be like, what if we tried to just like straightforwardly stick with Euclidean space? Exactly how far do we get before and what blows up in our face? But that's definitely worth pondering. So I mean, like in this case, you do sometimes get things in Euclidean space, but they're just not lattices. Yeah.
So I'm looking at these things and trying to think about the difference between Coxeter and Dynkin diagrams, especially because I guess in this case, we're looking at symmetries of lattices. We could describe them with Coxeter diagrams. The extra information here is this inequality thing, and that represents something physical about the lattice itself as opposed to the group of symmetries.
Right.
What is it if these Dynkin diagrams don't actually pin down the lattice itself? What are we hoping to achieve by adding this extra information?
So they pin the lattice down up to similar. So let's just talk about the ones that consist of a single thing, that come from a single diagram, not a direct sum. So then they pin down the lattice up to what I was calling similarity, meaning rotations and rescalings. So like if I made everything twice as long, the diagrams that I've told you about wouldn't know that. But apart from that, and rotations, which are even more obviously sort of something that it doesn't know about, that they do pin it down. So basically, when you hand me something, when you hand me a diagram like this, I say to myself, I need to pick 4 linearly independent vectors in R4, and they're going to generate my lattice. And then these 2 have to be the same length. I know they have to be the same length because of some stuff that I didn't just like revealed at the last minute, that when it's a single edge, you take them to be the same length. These 2 have to be the same length, but this one has to be square root of 2 times as long as that one. So now I know what the lengths of all of them are. And then I say, oh, this means that they're at a 60-degree angle from each other. These 2 are at a 60-degree angle from each other. These 2 are at a 45-degree angle from each other. These 2 are at right angles, and these 2 are at right angles. And so that's a lot of constraints, and that's enough constraints to completely nail it down up to similarity.
Okay,
it turns out.
but is it that one lattice can have several Dynkin diagrams? Is that correct?
Yeah, we've seen cases where the same lattice, like the CN lattice, is the same as the DN lattice. So yeah, so you can have cases where the same lattice can give you different Dynkin diagrams, and you can have cases where a Coxeter diagram has no Dynkin diagram, or where a Coxeter diagram has several Dynkin diagrams. I guess I'm repeating myself there. Yeah.
Probably leave it there.
Okay, so we should stop here. Thanks.